Note, I'd like to welcome the second session speaker, Dr. Lakshmanan sir. Sir, session is over to you, sir.
I'm Vishwa. Yeah. Good afternoon. Thiru, am I audible?
Yes, sir.
Am I
Yes, sir.
audible?
Clear,
Yeah.
clear, clear.
Thank you. Thank you, Dr. Thiru, for giving a brief introduction about me. First of all, I'd like to thank the Technology Information Forecasting and Assessment Council, TIFAC, of Vellore Institute of Technology, VIT University, Vellore campus. Thank you for the team for giving me this opportunity to deliver an expert lecture on this 5 days faculty development program on recent trends in power electronics. Uh, I like to thank the coordinators, especially my friend Dr. Thiru, because he was calling me and discussing, do you be the part of this event? Then I asked, what is it, the content as well as the presentation, which I can deliver, and what about the participants also? Then he said, electric vehicles. I said, okay, it's quite interesting. Maybe probably you have been working in the same area. So I once again thank the VIT team for giving me this opportunity to deliver expert lecture on this wonderful session, wonderful occasion. Thank you once again. So with this, I'm directly moving to this presentation. Is it fine, Dr. Thiru?
Yes, 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 yes.
Yeah, I'm going to share the screen. I hope the screen is shared and it is in full screen mode. Am I right, Dr. Thiru?
Yes, sir. Screen is
Yeah,
shared,
fine.
but not in PPT mode.
Now, please, would you please check it now? Because my side it's in full screen mode, PPT mode. Is it fine, sir?
It will come. It is in same mode.
Mm-hmm. And just stop sharing and sharing once again.
Yeah. Please do this.
Yeah.
Sometimes the delay will be there.
Yeah, sir. That's what window. Faculty share. Stop sharing. Now it's fine, sir.
Yeah, it is. It has come actually, but it is not a slideshow. You can able to see your slides, but not a slideshow.
Because my screen is showing as a slide mode only, full screen mode.
Wait a minute, sir. Shivam?
Yeah. You, sir, you can share your entire screen.
Yeah.
Entire screen. Okay.
Yes.
Okay. I'm going to unshare and then I'm going to share entire screen in this. Share. Now, please.
Yeah. Now clear, sir.
Fine.
Yeah.
Okay. Thank you. Once again to all the participants who have been the part of this today's 5 days FDP on recent trends in power electronics organizing by VIT University. Today I'm going to share some of the important concepts about the electric vehicles, powertrain, and then the power electronic converters, the role of power electronic converters, which plays a major part in the electric vehicle design. Especially, I'm going to talking about the DC-DC converter part, and followed by the various challenges and opportunities which are currently there in front of us in the field of electric vehicles. Moreover, I'd like to share some of our experience with EV, electric vehicle design and fabrication with our Amrita Vidyapeetham. We are focusing on different experts, including battery as well as power electronics and signal processing applications to EV. We have the multiple campus working from Coimbatore and Chennai and Bangalore. The faculty team, we are working together to develop such kind of EV. But the Chennai campus is very new, so we recently involved in the EV fabrication and the design, including battery management system, all those things. But our parent campus, Coimbatore campus, they have well-established EV research centers and labs. So I'm going to share those experiences also, in which it's useful for the participants of today's FDP. So I'm going to discuss about the basic history of EV as well as the types of electric vehicles and powertrain system, followed by what are the various challenges and opportunities we have actually, since we are talking about electric vehicles and also in future is going to play the major role, and maybe the government of India as well as the various public companies as well as private companies, they are working towards EV by reducing this carbon dioxide, but we have still some challenges and opportunities. So we are going to see the technical aspects of the various challenges and opportunities, followed by the important part, power electronics converters for the EV applications, specifically the DC converters. I'm going to touch a small thing about inverters also. Then the various standards which is currently available in the EV, and what are the future aspects with respect to the standards, because the standards are one of the major challenge we have to follow when you're going to design the electric vehicles with respect to the battery charging system, etc. Then there are some the recent the switching technology happening, because when you're going to use the power electronic converters, the switching devices are the major component. So the switching devices, we are using a very basic silicon and germanium based, but now the recent research is going towards to using some advanced gallium silicon carbide and GaN devices. I'm going to discuss about those changes and trends which are currently available in the industry, and how can we meet with like academic researchers as well. Then I'm going to give the battery systems also, then followed by conclusions. Of course, dear participants, the electric vehicle is not new actually. The trend started, the electric vehicle started from even long back actually. For example, in the first small scale electric cars were invented, but there are a lot of challenges as well as drawbacks also there by engineers and scientists, so that they were slowly moving towards, by the, when the year moves, the development was there. Especially in the 1832 as well as in 1890s also, the first EV was debuted in US, followed by the electric cars started gaining popularity among the people. But what happened in the 1920 onwards, there was a decline in EVs. Why? Because there was a oil revolutionary happened, so that the people started thinking using conventional oil-based conventional IC engine-based vehicles rather than the electric vehicles. So such kind of transitions were there from long back and recent trend also. So the EV is not new, especially then again there was a the fuel cost changing as well as the dynamic changes happening all over the globe towards the oil price and all. People started thinking moving towards EV. Moreover, due to the application of the conventional IC engine vehicle, pollution, the emission of carbon dioxide, global warming, so many issues are coming because of the populations keep increasing. Entire the globe, the countries were facing a lot of issues. So they started again thinking we can climb towards to EV. That is started from next generation of EV from the year 1970s. Then when you're going to start using this any kind of vehicle, there should be some regulations, right? Like government organization, government agencies, as well as the private bodies, follow some regulations. So the new regulations started coming from 1990 onwards. Then the major companies, automotive companies, they started working on developing the EVs. Then now the 2010 onwards, the electric vehicles started coming to the commercialized actually, in terms of a small two-wheeler to the three-wheeler rickshaw, auto e-rickshaw, followed by a small vehicle for the four-wheeler bus. Then nowadays they are working towards electric trucks also. So then the 2017 to 18, the electric cars started igniting because of the lot of initiation by the government of India, because the government of India is moving towards renewable based power generation basically, because based on the Jawaharlal Nehru solar mission as well as the other kind of missions motivating us to use the renewable power based RPG, renewable power based power generation. So based on that power generation, why can't we use the electric vehicles also, so that we can go for completely green energy, smart green energy based system. So the 2017 onwards, the invention of the electric vehicle, the research in electric vehicle started increasing, and still we are working on that in 21, 22, 23 also. So my point is, electric vehicle is not new. People are working now, but we have to, when we are going to do any research or any kind of modeling and all, we have to relook those kind of research already done in the field of electric vehicles. Okay. Now, the another aspects actually, before going to the technical part, I'm just covering 2-3 slides, which is connecting the concepts or the importance, the bridging that the reality of EV to the technical part. That's what this slide talks about, the CO2 emissions. Of course, there are two different types of CO2. We are currently facing the problems like direct emissions also there, and some indirect emissions also there. When you talk about the direct emissions, emissions, almost we can see there 24%, 25% example. The 25% is coming from the electricity and heat production, and especially the transport, there are a good amount of percentage of CO2 emissions are there. So we have to minimize it. Otherwise, in the next generation, already we are facing a lot of issues. Even if you are going to check the air quality index, like cities like Delhi and some metro like Mumbai and Chennai and all. Chennai is okay, but still there are some cities. If you're going to check the air quality index AQI, there are a lot of problems are there with respect to the emission of CO2. So the direct emission of CO2 is the one part. The second is actually indirect emissions. Again, the transportation is going to give a good amount of contributions. So we have to take the next step to take care of the CO2 emissions by the way introducing a smart green energy based electric vehicle. It's not conventional electric vehicle. I'm just telling the word a smart green energy, that is renewable power generation, solar PV, wind based. Completely the setup itself is smart green energy based electric vehicle system. We must work and we must move to that system. Okay, the another interesting point I'm going to connect with between the technical part in the electric vehicle is actually now currently we have grid. Yes, we are all working the academic as well as the industry research also there with respect to the grid. So basically we are going to classify the grids in 5 different types. For example, we can start with the high carbon grid. The name itself indicates that what is the meaning of high carbon grid. The high carbon grid indicates that the power generation is 93% is coming from the coal based power generation, like thermal based power generation. So such kind of grid we are classifying under the high carbon grid. Because there the emissions also there, because there the zero emission fuels are very 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 less, like almost 7% or less than 7% like that. So we are going to use the grid completely coming under the category of completely coal based, that we can call it as high carbon grid. The next we have medium high carbon grid, because like 27% or 25%. Then we have the medium carbon. Next we have the medium low carbon. Then the last category actually classified as the low carbon grid. What is the meaning of low carbon grid? The low carbon grid indicates that the power generation is completely coming from that renewable power based. There are 0% coal, of course a small amount of natural gas, and there we can note down that 97% of zero emission fuels happening in the case of a low carbon grid happening. So this classification of grid is very important when we are going to working towards the electric vehicle. Reason is I'm having electric vehicle, but if I use the electric vehicle in front of the or with currently equipped with the high carbon grid, again I'm not going to contribute the best thing to society. Again I'm indirectly or directly emitting the CO2. Instead, I'm going to use my electric vehicle with respect to the low carbon grid, which is coming connected only the power generation from the renewable energy sources. I may able to tell that, oh no, I'm going to provide the zero emission fuels is good amount. That means CO2 emission is very less. So the idea is the government as well as privates working towards to moving the entire systems to the low carbon grid in future. By the way, by connecting the low carbon with respect to the electric vehicle is going to give the fruitful results rather than high carbon grid. So this point maybe researchers are already working, but a lot of research opportunities are there with respect to the interconnecting this low carbon grid system to the electric vehicle. So those technical aspects also we are going to see in the upcoming slides. So the classification of the grid starting from high carbon, that is completely based on the coal based. Opposite side we have low carbon, that is completely depends upon the renewable power based system. Okay, another quite interesting point I want to emphasize here actually, yes, when you're going to charge the electric vehicle, for example, here we have 3 types of electric vehicle, that is battery electric vehicle, plug-in hybrid electric vehicle, then conventional vehicles. So when you're going to charge this battery electric vehicle as well as plug-in hybrid electric vehicle using this high carbon grid based system, again the emission level is almost, you can see H2 as well as the CO2 parameter is almost 11.17% or 11, almost 12 13 also sometimes. If you take the plug-in electric vehicle, it is also nearly going to the equivalent to 13, because the conventional vehicle actually 13% is there, but it's nearly equal to 11.17 to 13 or 12.2 to 13. That means we are not efficiently using the electric vehicles towards the sustainable development and the societal benefit. Still, even if I'm having the own e-scooter, if I'm going to charge that using the conventional high carbon grid-based system, I'm indirectly emitting the CO2 to the society. Then what is the solution? That's what, if you're going to use the charging this battery electric vehicle or plug-in electric vehicle, with respect to the low carbon grid based system, there we can see the emission level. That is 4.0, 3.9. So there is a large difference between 13 and 4.0, 3.8, 3.5 like that. That means we are supporting to the system when I'm going to use the electric vehicle, especially the plug-in electric vehicle, battery electric vehicle, which all connected charging through this low carbon grid system. So ultimately, the sustainable development, that is pure green energy based system, is happening only through developing low carbon plus electric vehicle in future. Let's see how we are going to progress. Then what are the advantages? So from these basic slides, like 2 3 slides, no fuel, no emission, of course. Then of course cheaper to run. Then wide range of speed because of the development happening with respect to the technological power converters and battery and all. Wide range also is possible with respect to EV. Then a lot of health benefits because of the air quality. We are not disturbing. CO2 emissions are very less. And of course, the another advantage is actually we can connect and we can correlate the EVs with respect to the power grid. We are going to see that at this vehicle to grid system, V2G applications. So those are the major advantages we are having directly as well as indirectly when I'm going to use the EV in the EV powertrain system. All right. Then how do we classify the vehicles? Of course, we have a very basic classification into 3 types. One is conventional IC engine electric, internal combustion, then followed by hybrid electric vehicle, then pure, that is battery electric vehicle. If you're going to take ICEV, internal combustion, then micro hybrid. Actually, we are not putting as micro hybrid also. I'm just putting sometimes, for laboratory purpose, we are just developing such kind of micro hybrid also. So that's what the classification comes under the internal combustion. When hybrid, we have actually mild hybrid, then full hybrid, then extended range, then series, parallel, plug-in. A lot of because of the way how they are going to connected with the conventional petrol or diesel with respect to the battery, then how the motors are happening, power converters, power transmitters are happening. Based on that, we have different classifications followed by mild, full, in that itself, extended range, series, parallel, plug-in, HV, etc. Then the pure side, we have actually battery electric vehicle, then fuel cell electric vehicle. So battery electric vehicle, there is no connection with that IC engine, like there is no fuel and all. Only the source is the battery, in which the entire power transmission is happening in the case of battery electric vehicle, followed by fuel cell electric vehicle. So major classification, because some of the references, research papers and books that given different classifications, but I'm just giving the overall idea about the classification of vehicles with respect to the EV. Then again, before going to the technical part, what about efficiency? That is, you have that is also simply called as a tank to wheel efficiency. Tank to wheel efficiency. If you take IC engine vehicle, we are going to have 100% efficiency of the petrol tank. Then when it's reaching to the engine, only 20%. What about there are the huge losses happening, followed by from engine to drive lane system. Again, there will be reduction in efficiency. Then finally coming to the wheel, only 16%. But when suppose the same IC engine vehicle we are using for long duration of 3 years or 4 years, again efficiency is very less because already engine efficiency reduced. But going to the other side, battery electric vehicle, if you are going to have 100% on the electricity, then followed by coming to the battery, there is no huge loss because we have the very good battery system to store, followed by the drive system. Yes, the power converters are very compatible, which is connecting the battery and motor drive. If it is a DC, we are going to use the DC to DC converter. If we are going to use the AC induction motor type, we are going to use 2 types. That is, one is DC to AC followed by rectifier. Inverter. Then we are going to have the AC motor also. So the efficiency reduction with respect to the battery and motor drive is not very high. It's only accepted range. Also, a lot of research is going the way we are going to design the power electronic converters, all those things. Then what about wheel? At the wheel, we are having only, so we are going to have 72%. So the tank to wheel efficiency with respect to the IC engine, the battery electric vehicle or pure electric vehicle is very good. So that is another reasons we are moving towards the EV. Meanwhile, the emissions also, because the conventional vehicle, we have carbon monoxide as well as we have sulfur oxides. We have actually, pollution magnets. Then a lot of emissions are there, especially the CO is very high and sulfur oxides also very high. But when you compare to the IC engine, the battery electric vehicle is having there will be a very less emissions which is happening with respect to the EV system. Then, if you're going to talk about the EV, like a different grid, like high carbon to the low carbon grid, as well as the in the previous slides we have seen the charging, all those things. What about the energy diversifications? Yes, we have different kinds of vehicles on the right hand side. We have left hand side. We have different types of sources. But how do you take this energy diversification? Because this is very important to understand about the vehicles, not only electric vehicles, generally the vehicles. If we talk about the conventional IC engine, actually, yes, liquid fuels, petrol and diesel, they take major place. Of course, the natural gas also can support. Then followed by, if you go into the hybrid electric vehicle, both gaseous fuels as well as the liquid fuels. When you talk about the plug-in electric vehicle as well as battery electric vehicle, the pure electricity is coming. And then if you're going to talk about the fuels electric vehicle, hydrogen is the major source. So what I'm trying to say, that the energy diversifications is very important when you're going to work on that conventional IC versus electric vehicles. Because electric vehicle, since we're having two types, like broadly pure electric vehicle as well as hybrid electric vehicle or plug-in hybrid electric vehicle, the energy diversification is happening between the sources to the vehicle is very important. So because this going to play the major role, the way we are going to use the battery management system as well as the role of power electronic converters, as well as the design of all the required thing, including control techniques, all those things which depends on this energy diversifications. So we must follow that. We must understand that if you are going to plan to work in the field of electric vehicles. Right. Then what are the challenges? The challenges, opportunities which are there in the electric vehicles. I'm just putting in four different categories. One is actually technical aspects. The second is infrastructure aspects. Then policy, market. Because since we are developing an electric vehicle and bringing to the society, anybody can use, or this can reach to all the common people. Then all the people, there are some challenges and opportunities. Of course, opportunities also there. So when you talk about the technical part, yes, very, very important point is actually efficiency of the batteries, the range energy. Suppose I'm having a car, electric vehicle, so I'm going to travel 400 kilometer, but my battery is able to possibly give the supply to my motors only range of 150. So the range annexity, efficiency of the battery is the very, very, very important. And also, as I said, the driving range, the range is on. Then the charging time. Yes, I'm going for very urgent work. I want to travel 400 kilometers, but my the battery got disappeared. So at that time, what is happening? I want to move to the charging time. So that means my charging time should be less as much as possible. Even I don't want to wait more time also. Like I want to charge the battery, like I'm filling the petrol, like 2 minutes or maximum 5 minutes, like that. So such kind of technical experts are there. We can think about that, how to improve those. Like I want to charge with less time. I want to increase the range. Also, I want to increase the efficiency of the battery. So many technical challenges are there in all the domains. Not only in the engineering field, like sciences people are working to develop different materials as well as increase the efficiency of the battery. Followed by the ranges are happening. Followed by charging times are happening. Followed by safety. Those things. Then what about the infrastructure? Yes, this is another important thing. Just think about that, whether we have sufficient charging infrastructure. Now people are started using EV. Government is also initiating 2027. Almost we are going to replace some percentage of EV rather than the IC engine. Whether our system can support, first of all. For example, suppose Chennai, we can take an example. There are 1 lakh vehicles are there. People are going to use 1 lakh vehicle example. Suppose they want to charge the 1 lakh vehicles during this night time, not in the peak time. Whether our grid system can support to charge 1 lakh electric vehicles at a time. Whether do we have such a whether charging infrastructure? No. Answer is no. Now we have a very, very quite less number of charging infrastructure at the charging stations, and we are charging. But when in future everybody started using EV, like car, e-rickshaw, or auto, or cycle, different kind of vehicle, our charging system should support for that. We have to focus all those areas, not only like one aspects. Of course, our researchers are looking at different domains. So the charging infrastructure is another major challenge. It is major challenge for all the government as well as public, including the private companies also. We should have such kind of charging infrastructure, because our load, even the summer peak time, for example, last month we were in the summer period, we were started using AC air conditioners. So there are a lot of load disturbances happening, so that the power cut down were there. But under the condition, once we include the vehicles also, whether how it can support the system, how the system can support, right? Like the infrastructure should be developed. The engineers having a lot of roles to develop such kind of charging infrastructure. Of course, fund is required and government support is required, space is required. So many things are there. And again, battery, like smart grid. Yes, we are moving towards renewable based power stations also. So the synchronization of those kind of efficient, smart power generation with respect to the electric is also another major challenge, because the load, the range of loads, the diversity of the loads, the power diversity of the loads. So many issues are there. We're going to talk about the smart grid also. Then another important infrastructure challenge actually we have is nothing but battery recycling. Yes, now we are using cell phones, we are using a battery. 1 year or 2 year we're using, then we are just throwing out the, whether we are properly recycling the cell phone battery itself. No, answer is no. Maybe maybe some of the teams are working, but generally I'm talking about, we are not just only putting one of the corner in our house. So in future we are going to increase the electric vehicle. The battery is the main source. How do we recycle those unwanted, unused batteries, or those batteries got expired? There should be a proper recycling plan should be developed, and we are going to start recycling again. There are human assets are there. A lot of infrastructure challenges are there. We don't have any sufficient or the recycling concept itself with respect to the electrical. So we have to develop. Then coming to the another challenge, actually we have policy. Yes, government is telling that tax relaxation as well as the promotion of the EV, and so many issues, so many policies are coming up. But that can suitable to all the people, like, because the cost is a very major part. EV cost is a major part. The main source battery is the main. As also the accessories, power electronics, power converters, entire system is the very major challenge. So the taxation is reaching to everyone, and the subsidies and also tariff policies. I'm going to buy the electric vehicle, then I'm going to use for a couple of years. So the tariff policies is not clear, or it's maybe clear, but it's not reaching to everyone. So we must take the initiation, like engineers and researchers, by developing some, research articles, or maybe to reaching to the with different ways. So the policy should be there. Of course, then finally the another important challenge we have actually called as market. Market means we don't have a very the advertising or marketing the EV. Yes, we are working now currently, but I'm talking about very very, like example, we have big showrooms to sell IC engine. Now even the Tata is giving the Tata Taigo, all those things, but the marketing is still very less. And also when I'm going to use the EV for, I'm going for testing and certification, a lot of processes are there, and financing is also there, and the raw materials for the batteries. So and here I'm giving only the very 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 general points, talking about the challenges, like technical experts, infrastructure experts, policy, as well as market. But if we're going to take these challenges, definitely we can also convert into opportunities. By that, opportunities we're creating only by the researchers like us, like academic researchers. We can collaborate with the industries, and we can open the opportunities like a team. If they're going to work, we'll get solutions actually, in all the experts, not only this limited 4 experts like technical, infrastructure, policy, and market. The wide opportunities are there in the field of electric vehicles. That's what I'm taking. Just I have taken some time in this slide, but those who are planning to work in the electric vehicles, other than the technical experts, other than the designing of power electronic converters, other than the designing of sensors, other than the modeling of the system, there are some other challenges, opportunities also there. We can work in those areas also if interested, like technical, infrastructure, policy, and market. Yes. Now let's come into this power electronic converters. So maybe this is generalized the block diagram, which shows that different converters are there, different power electronic converters are there. Actually, we have actually a grid followed by a electric vehicle with wheels are there, including the transmission system. Uh, First, we'll see the sources. Actually, here we have battery. Also we have actually super capacitor. So different types of sources are there. Suppose I want to go for fuel cell. Yes, fuel cell is also another kind of source. So sources are there. According to the source, we have to select the converters. Also, according to the load what we are keeping, drive system. Suppose I'm going to use a motor, kind of a AC motor. So I have to use. Similarly, I'm going to use the DC motor, because electric motor for the electric vehicle is the another very broad. I'm going to cover one slide on this electric motor for the EV system, motors for the EV system. So the power converters plays a major role. For example, in this slide, we have actually a battery, and the opposite we have supercapacitor. So we are going to have this kind of a battery or supercapacitor. We must use a DC-DC converter. DC-DC converter. And then the DC converter, what is the role? Is converts a DC voltage, that is a fixed DC or to variable DC, followed by our the input voltage. We are going to have less voltage. We can boost up, like boost converter, like buck boost converter. Depends upon the classification of the DC-DC converter. We are going to see that. So the DC-DC converter is we are placing, followed by we are going to maintain the DC voltage using the DC bus. Then depends upon the motor. We are using an inverter here, which converts DC to AC, a three-phase inverter, like multi-level inverters, for starting from 2-level, then multi-level inverter. Because now the recent research is it's already happening. Multi-level inverters for the role of power converters in EV applications is another major point. Suppose you are going to use only the DC motor, we are using only another kind of DC-DC converter. So the power electronic converters, especially DC-DC converters, is there with respect to the. Even we can use the power electronic converters in the charging side also. Suppose I'm using the grid, I'm going to charge the entire system. So there also there are appropriate power electronic converters we must use. So the research opportunities are there widely in the face of power electronic converters for the motor to the between the motor and to the source, like battery or supercapacitor, or source grid charging point to the battery. So those areas, the opportunities are there. So now I'm going to talk about something about the DC-DC converters. So basically, DC to DC converter is a power electronic converters is a compatible device between the input DC to the output DC, because the load requirement is different, but the available source is different. We have to make the compatible between the source and load by keeping a simple DC-DC converter. DC-DC converter which also converts and control of the input DC to the output DC. Basically, we have three types of DC-DC converters. One is actually unidirectional, bidirectional, as well as wireless power transfer. But what are the main objectives in which researchers are working towards actually? When I'm going to talk about DC-DC converters, the main components are the power electronic device, switching device, especially IGBT. Then followed by the components like inductor and capacitors, because we have the filter. Also, we must have the inductor. So the number of component which is presenting in the DC-DC converter, like, means we have to reduce the components and switches as much as possible, so that we can get a very compact DC-DC converter topology. Then the second challenge actually we are going to have actually the development of the pulse width modulation, like switching, as well as we are going to use the switching pulse width modulation. Losses also there, so those concepts can be developed. Then the switch selection as well as the gate driver, because depends upon the converter, a lot of hardware designing, interloop design, including with FPGA, as well as connecting the DSP or some D-space properly. We have to design the hardware and using proper gate driver. Then there are two types of switching, again, soft switching and hard switching. And I'm going to talk about the soft switching, again, to reduce the losses with the different range of load conditions. Those also another challenging. Then wireless power transfer, yes. Research is also going in the field of wireless power transfer, especially the development of wireless power technology using DC-DC converters also is happening in the field. So these are the major areas. It's currently there as a problems. We have to find out the solution. We are going to implement the DC to DC converters for the electric vehicle applications. So how do we classify? Basically, we can classify DC-DC converters as two things. One is non-isolated, the second is isolated. The non-isolated covers very conventional things, actually buck converter, boost converter, buck boost converter, cuck converter, and SEPI converter. Especially the input voltage is very less battery. We want to step up, you can use the boost converter or buck boost converter. Similarly, that depends upon the converter which is a requirement. And followed by interleaved DC-DC converter, then multi-port DC-DC converter. The multi-port DC-DC converter is another part of the DC-DC converter, which plays one of the recent research is happening multi-port DC-DC, because it has a lot of advantage compared to conventional converters. Another side, we have actually isolated DC-DC converters. What are those? Yeah, flyback DC-DC converter, followed by yeah, bridge type DC-DC converter, then push-pull DC-DC converter, forward Z source. I'm not putting the other major classifications here. Only what currently we are working in our lab. I'm just putting those classifications only. So isolated converters means there will be a isolation part is there between input and output. Then when we talk about the bridge type, the full bridge and off bridge are the very basic classifications in which available in the case of the DC to DC converters. So let us first take a first example, non-isolated category in that conventional category, particularly boost converter. Of course, this is a simple, very clear circuit diagram of the boost converter. They are keeping input as the battery, then followed by inductor, then a Q is a switch actually, then followed by a diode, then filter circuit is there, then it is connected to the electric AC motor through the inverter. So the DC-DC converter is a boost type converter here. What is happening because of the inductance present on the input side, the input voltage you are going to supply, then output will be getting based on the duty ratio in which we are currently working. That is, output voltage V0 is equal to V in by 1 minus G. If you are going to work on the 50% duty ratio, you will be getting double of the input voltage. It's a very basic operation of the DC to DC boost converter. Lot of textbooks and research papers are detailed explain the operation of the DC boost converter and other converters also. You please refer it. I'm just giving overall idea about the DC converters of the boost type. What are the advantages? Of course, very simple circuit. We can design our lab also. Most of the academic institutes research labs, definitely there will be a presence of, there are some prototype models also there because it is used for the undergraduate lab purpose also. Then low cost, but control circuit is also very simple. We are going to use the closed loop, especially current mode control is very simple. Then the current mode control itself, then the very old technique, sliding mode control, so many advantages are there. Very easy to implement the DC-DC converter with improved dynamic performance. Reason is, when you're going to work on the DC-DC boost converter, stability is another major issue because when you're going to check the transfer function analysis, there will be a location of the zero at the right hand side. So RHP problem is there because of the presence of the passive elements. So the stability is another major issue. For that also, there are proper control techniques are already there. So DC-DC converters we can use very well in the electrical. But what is the problem is actually the voltage gain also is very less, followed by a filter capacitor is quite large because since the size is increasing a lot. Then the ripple output, that is output voltage, and also the inductor current having a good amount of ripple. So we have to use a proper filter mechanism to remove that. So these are the very simple disadvantage, but it's quite compatible to use the DC-DC boost converter. Then the another category is nothing but actually interleaved four-phase DC to DC converter. Like what is happening in this case of DC-DC converter? There are input is the battery, example of the DC, and output side we have used AC motor, so that inverter is placed here, and before that there's a filter capacitor. But the way the four switches are connected with respect to the inductor is called as the interleaved four-phase DC to DC boost converter. The problem with that inductor current ripples in the previous boost converter was minimized here, and also voltage gain is improved. And control techniques also very simple. You can implement current control techniques also, but the problem is actually switching loss because of my Q1, Q2, Q3, Q4. Also, components count is increased. So when you're going to compromise the one axis like voltage gain, we are getting another problem like increasing components count. That is what the research engineer is going to compatibly design the DC-DC converter by taking all the considerations like voltage gain, reduced ripples in voltage and current, especially filter capacitor output voltage or inductor current ripple, then the switching component, all those things. That's the major thing. Then the resonant actually. So when you're going to use this boost converter resonant circuit, soft switching is happening, so losses are minimizing, especially the electromagnetic interference are getting reducing, and the size is actually very good size and very compatible also, and the heat sink size is much reduced actually compared to the previous kind of converters. So the boost converter with advantages I'm just explaining here. With resonant type, and what is the disadvantage? Actually low voltage gain and not suitable for the high power conversions. And followed by we have actually the full bridge. This is actually a category of isolated converters. Here we have the input is battery, outputs, we have the induction motor, AC motor, so that we are using this inverter suitably, like to 2-level or 3-level, etc. Depends upon the type of inverter we are implementing here. So in this isolation converter, what is the major advantage is actually the step up, high voltage step up is possible, which also the efficiency is increasing, and the stress on the circuit is reduced, and isolation is happening between input and output. Only thing again here, the problem is like a filter capacitor is the size is where also stresses are there when you're going to see the current waveform as well as the switches, the stress. We can able to identify large current stress on the switches as with full bridge. But full bridge also mostly used for the research purpose, and we are getting some waveforms also. And this is another kind of a slide which can discuss about converters, especially powertronic converters in different aspects. Like already we have seen DC-DC converters where we started actually battery pack. Earlier we have seen battery or supercapacitor, followed by the type of motor we are using a type of a DC-DC converter, type DC-DC converter. But coming to the left-hand side, it's quite interesting actually. Left-hand side, because we are going to talk about the charging side, the role of powertronic converters also. So in left-hand side, we have the grid, followed by we have 3 types of charging. Basically, in EV, we are classifying as a level 1, level 2, level 3. So level 1 means it takes 120 volts AC, basically using in home or office applications. Level 1, and it's mainly onboard charging. And the next category we have actually level 2. It's voltage, actually 230 voltage we can use, and this may be placed in for the public or private purpose also. They are also onboard charging. The another category is very important, that is a level 3 off-board charging. So the types of charging like level 1, level 2, level 3, maybe we can put it in other words, onboard charging, off-board charging. Accordingly, there will be a charge controller is there. Accordingly, the powertronic converters, because we are having actually onboard and offboard charger in which the suitable powertronic converters can be used, because the unidirectional power flow or bidirectional power flow. See, a very interesting point, because there are different types of levels of charging, followed by different types of power flow happening with respect to the powertronic converters. So what I'm trying to say, when I'm going to use the different charging system, level 1, level 2, level 3, with respect to the charging controller, we have to use appropriate powertronic converters. For example, when I'm going to use a level 1 charging, what is happening? We can use first convert that AC to DC. So we have to use one rectifier, AC to DC rectifier. So what kind of rectifier? Again, the question. Yes, we have to design that. We have to select appropriately our voltage and other requirements. Then before going to the DC battery or the DC converter, we are going to use a PFC, power factor correction converter. So followed by we are going to use the DC converter. So the DC converter can step up the voltage, especially boost converter, then it's feeding into the battery. Or we are going to use the different, like we are seeing now, different converters. We have seen the converters with respect to the electric motor side, not into the charging side. The charging side also, level 1, level 2, level 3, or onboard, offboard charging, the suitable powertronic converters can be designed. Based on that, the standards also possible. We are going to see 1 or 2 slides in standards also. So this slide also similarly, like we have seen the DC converters, but this part is explaining clearly about the different levels of charging, level 1, level 2, level 3, with respect to the battery charging system. Charging system, like we have a very basic grid. So based on the grid, if you're going to take a common AC bus, that's actually called as AC bus charging system. For example, what's happening? We are taking the grid, and then we are converting that AC to DC. Then the DC-DC converter followed by the charging port 1, it is going charging port 1. So we are maintaining a common AC bus at the grid. Further, we are using a rectifier. Why the rectifier is used? Actually, it's also called as AC to DC converter, right? So the AC to DC converter converts the DC, and that we are suitably balancing, like high efficiency, because we want to get a proper DC output voltage at the charging port 1. So like that, if you're going to increase the port 1, port 2, port 3, port 4 with respect to the common AC bus, then we can call it as a common AC bus charging system. Then another category we have actually DC bus. instead of putting a parallel rows, let us take that grid, then we can use the converting that AC to DC, then maintaining a common DC bus. Accordingly, we can take charging port 1 using a converter 1, charging port 2 using converter 2, charging port 3, charging port 4, like that. So this is a common DC bus charging system. So both having a lot of design and control challenges, because the power electronic converter switches are there. Compatible design should be provided to take the challenge of this AC bus and DC bus charging system. Right. So these are the very basic things which is talking about the charging side. Now let us work on the discuss about the standards actually. Why the standard is important? Yes, um, the standards is going to give the very clear idea about the electric vehicle to all the people, from the industry, from the government, from the public. So they're connecting all the side. So basically, the pro charges we are using different way. Example, connected to vehicle we are using. Then the charging limits as well as the communication protocol side. Then also so many parameters need for the standardization. Basically, yeah. Basically, we are based on the charging. We are using like level 1, level 2, level 3, right? Accordingly, we have single phase 110 voltage, then followed by 230 voltage, or three phase 420, etc. Also there. Similarly, DC side also there. So in the voltage range, we need a we standard. Similarly, for connectors, similarly for the protocols between the charger and vehicle, then the other kind of environmental EMI, all those things also the standards are there. In India, actually, we are using a Bharat Department of Heavy Industries. They have developed the charging. Still, there are some standards are developing stage. So, Department of Heavy Industries and Government of India are taking to develop the standards for our Indian system. Some of the very standard are given by developed by different industries is shown here. Japan actually they started JARI, Japan Automotive Research Institute. They developed a standard called as Chakdamo. It's nothing but simply let's take coffee. Let's take coffee by a word. Let's take coffee by uh, coffee by the word. Then followed by China. They are working on called as GBT charger. Uh, GBT charger. Then followed by IEC, that is International Electrotechnical Commission. They started working on the uh, um, uh, European standards. See, IEC 61851, they are giving for the system A type, which is up to 500 voltage DC. Then we are going to increase that voltage up to 1000. They call it a system C charging standard. So European units. Then of course US also started developing SAE, the Society of Automotive Engineers. They are putting standards for level 1, level 2, level 3, and system C, all the including vehicle to G, grid to vehicle protocols, all those things. And our in India, actually, Bureau of Indian Standards, they started working on this standards, especially Department of Heavy Industries, IS 17071, then followed by the other kind of methods are there. Then Department of Heavy Industry working on Bharat charging. Yes, for the AC we are putting AC 001. For DC we are putting DC 001. So still the development of charging standards for the EV in the different role is the different part is very important. Is working on that. Those who are planning to work on standards, they may refer the websites which is like shown by the standard bodies like from the Japan, China, followed by SAE, and then and also our Indian standards like Bureau of Indian Standards and Heavy Industry. Those are all very interesting to learn as well as important to learn as engineers. Next, I'm slowly moving towards to the switches side, because we have seen the role of power electronic converters. Specifically, we have seen the DC-DC converters to connecting to the drive system, electric motor system. On another side, the charging side, we have a common AC bus or common DC bus. The power electronic converters are taking a major role. Okay. Conventionally, the silicon and based, especially silicon IGBT or silicon MOSFET they were using. But when the problem using the silicon MOSFET or silicon IGBT, actually efficiency they're maintaining good, but again the switching frequency, very important point, switching frequency. The switching frequency we can able to use maximum 50k, 30k to 40k or 50k like that. but low price, we agree, low price, and also very reliable and all. But because of the development in the field of semiconductor, the very the wide band gap semiconductors, or simply called as WBGS, their family called as silicon carbide and gallium nitride, SiC and GaN devices. So the SiC and GaN devices changing the entire the role of semiconductor industry, especially this power industry, power electronic converters like switches, power semiconductor switch. I'm not talking about our low power VLSI, like I'm talking about low power electronics. I'm talking about high power electronics, high power electronics. So here the silicon carbide and gallium nitride playing the very, very important crucial role in the currently, because good amount of efficiency. Reason is able to use good frequency range up to 5 gigahertz. Sometimes more than that also depends upon the applications, and very easy to handle. So many advantages are there, and power density we can use up to 50 watt per inch cube. So, but cost is very high. Very high means now cost is also under the compatible change, but generally compared to the conventional silicon based semiconductors, the wide band semiconductors WBG plays a major role by reducing, increasing the cost, and the packaging also there. So the wide band devices are suitable for the electric vehicle. That's a question now, because wide band devices are using for the smart grid applications, other things in the previous sense. But with respect to the electric vehicle, because electric vehicle power converters are playing major role in both way, motor side as well as charging side we are using. But use of this wide band semiconductor, whether any the revolution is happening, yes, it's happening because of using this wide band gap semiconductor devices like silicon carbide and gallium nitride based devices in power converters, which are connected with electric vehicle. A lot of significant changes are happening in the industry. So, for example, if you're going to use silicon based boost converter, as well as actually the BC shows the boost converter, then the MDIB shows another kind of boost converter, that is interleaved boost converter. Okay, so the two types of boost converter, using the silicon as a device, efficiency is almost reaching to 92, starting from 80 or 81 with a different frequency range. Even for the 80 kilohertz, we are reaching only boost converter 81 percentage, or interleaved boost converter reaching only 85 percentage, 80 kilohertz frequency. Especially for the low frequency 20 kilohertz, we are reaching for the boost converter only 87 percentage. Of course, the interleaved reaching to 91. What about when I'm going to use the silicon carbide based boost converter? That is having the very good efficiency change. That is when the frequency range from 20K to 80K, like 20K we are reaching 94, and 80K we are reaching almost 93. And interleaved boost converter also showing the good efficiency with wide range of frequencies. That is what researchers are very closely working on, the using this silicon carbide as well as gallium nitride based devices in the electric vehicle. I want to show one more slide actually. This slide is giving with respect to the electric vehicle itself, because the usage of SiC devices, SiC technology is usually called as SiC technology or GaN technology or WBG technology, right? Wide band gap semiconductor devices, right? So, the percentage use actually, earlier they were using this percentage use for the rail as well as power factor correction applications, or motor drive system, or oil and gas they were using. But EV, electric vehicle, including onboard charging, sir, including onboard charging, the percentage is increasing. Now, 23, we have to check. It's maybe the percentage is increased. The use of the silicon carbide, gallium nitride, we used to call it simply actually the market capitalization. Yes, the market capitalization of this silicon carbide device in current trend, especially for the EV, is increasing. So we can also now take the opportunity to involve silicon carbide devices with our research, and especially electric vehicles, and see the performance of the power electronic converters. Of course, there will be a effective performance with a wide range of frequencies using this silicon carbide and gallium nitride based power semiconductor devices. Yes. Now I'm coming to the another part of the presentation. I'll take all the discussions, all your queries during our end of the presentation. If any queries, please note down. I request participants can note down the queries. We'll discuss. Yes, uh, now vehicle simply called as V2X. Yes, sir, I'm going to use, future is going to play the major role electric vehicles because of the various promotion of the government, private and the public, as well as the development in the field of power electronics, semiconductors, as well as the development in the field of smart sustainable development. Yes, Dr. Thiru, am I audible?
Yes, in between
Yeah,
some
fine.
snack, audible,
Yeah,
audible.
that's what because there was
Yeah.
a slight network change in my home.
Oh,
That's
okay,
what.
okay. No
Thank,
issue, no
thank
issue.
you,
Now it's
thank
okay.
you,
Yeah.
thank you. Fine. So, how do we optimize these vehicles with respect to the various nearby things with around us? Yes, we have loads, we have the grid, as well as we have the vehicle, we have the homes. How do we smartly optimize this vehicle to the different concepts? That's what V2S technology. People might already working. I hope this area is very quite well. I'm just giving I mean, like the generalized projection of this VTS technology. First of all, vehicle to grid technology. Yes, the vehicle to grid technology is very much useful when you're going to talk about the sharing the load, or no, sorry, sharing the power between this different, like peak time and off peak time. Because when I'm going to use the EV during this morning office time 9 a.m. to evening 5 p.m., my vehicle is ideal. Sometimes 4 hours it is charging, remaining 4 hours it is completely ideal. So why can't I use this my vehicle to supply to the during the peak load demand, to meeting the load demand which is happening in the peak hours? It's possible. Similarly, I can also use this concept to the meeting the load requirements of my home. Meeting the load requirements of different load, because there are mines, the people are working. So if the mines is very disconnected from the conventional city or town, so there the power requirement. How do we take up the power requirement? Only those kind of sharing or this VTS technology, or maybe I want to share the the concepts with respect to vehicle itself, or smart charging itself. So those broad areas simply called as VTS technology, like vehicle to grid, vehicle to load, vehicle to home. What ultimately we are doing, we are using this electric vehicle which are not in the use condition, especially office time hours, for the other purposes, like to meet the load demand, or to meet the load which are very much away from the natural, very much away from the conventional usage. For example, mines or other kind of places, or in the home itself. I want to use these concepts to electrifying the home for different purposes. So those things are very, very, very important. That's what I want to cover it. Next is actually um, next is actually challenges in the VTS technology. So when you're going to implement this VTS technology, what are those challenges? Yes, of course. The first challenge we are currently having is nothing but market and regulation. Market and regulation. What is this market and regulation? Because whether we have proper regulations as well as marketing to use this concepts VTS technology. Similarly, the technology development, actually, because of there will be a lack of standardization, because we are going to connect this vehicle to grid, or vehicle to vehicle, or vehicle to home. Proper standardization should be followed, because the ratings, the loads are different. The connection, the compatibility is very challenging, and the communication protocols also very much important when I'm going to use this VTS technology. So, but still, we are having this communication protocol. Even it is not having uniform communication protocols. Similarly, the awareness also very less. Now it started coming, but suppose a big apartment having 1,000 houses are there the awareness is very less. So how do we optimize these BTS concepts? So the major challenges which are there, actually, market and regulation, and also technology development, and then there is users engagement. um, you, how do we rectify those challenges when I'm going to take over this mm, vehicle to vehicle technology? Yes, of course. As a researchers, academic researchers, and industry people, we have closely worked with the public. Like we have to educate them, as well as we have to give the importance that how the electric vehicles can be used in the best way, because every day the challenges are happening with respect to the load and generation, power per generation load. So how do we meet, especially in the summer time, to meet such kind of peak load demand and all? This concept is very quite challenging, but quite possibility. But the connection is very challenging. So those awareness we have to create it. Policy should be developed, sanitation should be developed, communication should be developed. Also, other things should be developed to meet this weight technology. Then to promote these things, actually, our government of India is working on the National Electricity Mobility Mission, that is called as NEMM. Under this mission, the development of EV, actually the main idea is clean transportation, followed by a very effective charging infrastructure, also the proper security and environment to meet the cleaner objective. That's what the major objectives everybody knows, actually. So already in the government of India started JNNMSM, Jawaharlal Nehru Solar Mission. They are almost working towards to developing those kind of systems. Uh, followed by now recently this national electricity mobility started taking place. So how we are going to connect, as well as uh, learn from these missions, and how do we come up with this possible uh, outcomes with respect to the uh, national electricity mobility mission. Followed by we have a national smart grid mission, also the renewable generation. See, all are focusing on the development of low carbon grid, connecting with EV. Similarly, the reduction of greenhouse gas emissions and improved air quality. So all coming to the only the common point where CO2 emission, greenhouse gas emissions, improving the air quality, like air quality index, like air quality, followed by completely renewable based power generation, then connect generation of smart grid system, then EV. So all connect to the common point. It's called as the development of low carbon grid. That's what the enhancing the national security is very important, followed by the other environmental aspects. So those things are there. So our researchers, we can work by fulfilling this national electricity mobility mission, followed by national smart grid missions, then developing the low carbon grid. Ultimately, that's our important point. Then batteries, yes. So we have seen in our previous slides, the battery is the main source of the electric vehicle, because the electricity, the battery is the main energy supplier up to the drive system, transmission system, right? So battery, also the development of the battery for the EV is not new. Like we have seen the first slide, when they started working in 1830 or 1850 or 1920 itself, or 1970 itself, parallelly, whenever people are working towards the EV, they are also working towards the battery, because there are so there are how do you sorry, the research is happening with respect to the battery also. It's not new. Why? Because when working on the development of the EV, also material side, there was a good amount of researches are going. So the battery is the main very very important point. What are the different types of battery? Lithium ion battery, yes. Similarly, sodium, and also like an advanced lead acid battery. Like different types of batteries are there. What is the important thing we have to focus of the battery? Suppose we have to, first of all, high efficiency. It should have long life. The life cycle should be improved, and the safety should be protected. Also it can support the entire EV system without any problem. The driving range should be increased. Also the safety should be ensured, and the core materials required for the battery is very important. Then once the life cycle is completed, recycling is also there without affecting the common people. So many challenges are there to create any type of battery. That, for example, you take lithium ion battery. Lithium ion battery is coming almost 5,000 to 6,000 cycles with efficiency of around actually a good amount of efficiency. But when you talk about you want to increase the cycle, when I'm going to increase the cycles, so at that time lead acid battery also not suitable. Lead acid battery actually it's very quite range of cycles as well as with less efficiency. But the vanadium batteries and all is going to give increased cycles with medium level of efficiency. Suppose in between we have actually sodium sulfur batteries. Sodium sulfur batteries okay because they are having the cycles between to the between to the lead acid to the vanadium battery, but also the medium range of efficiency. So we have to technically look into that. We cannot select simply a battery for a suitable our EV because uh, every battery has their own characteristics because of the charging, discharging, cycling, as well as efficiency. So suitably we have to select. A lot of research is going in the field also. So it's a interdisciplinary research nowadays because we have to provide the sufficient data to find out the suitable battery also. Who means like power engineers as well as the electronics engineers and all. Then the mechanical engineers are going to provide the materials as well as the chemistry people. They're going to working on the synthesis of materials and developing a battery. In our institute, we developing the battery for the electric vehicle in our lab, chemistry lab. So we already taking the basic lithium-ion battery and lead acid battery only, but we started using the different cycles by testing with different ranges. But we are in the process to get some good results. So the lot of research opportunities is there for the electric vehicles also. When you talk about this, yes, Make in India is another important thing we are currently following in our country. The lead acid battery, we take lead acid battery, we are using actually. Uh, uh, Generally, we can use the lead acid battery, but we have to see the drawbacks also. Similarly, when I'm going to take up a lithium battery, the large power range transportation is required. There we are going to use this lithium-ion battery. Uh, Lithium-ion battery followed by flow batteries. We have actually flow batteries in the sense for the megawatt range we are using flow battery. Then it's all interconnected. The battery technology is very much important to develop the electric vehicle system. Also, a lot of associations are there. Society of Automotive Engineers, SAE, as well as IESA, and they are also closely working towards to the major battery manufacturers, EV manufacturers like Tesla, Panasonic, as well as the other kind of GE and all. So they are also developing very cost-effective, efficient battery with giving long life also. So when you talk about this battery, once again, lead acid battery, as we seen just now, cost is important. So the battery, the performance is going to, that means the performance metrics is closely coming towards the uh, like state of charge, as well as the depth of discharge, as well as the cost, life cycle, efficiency, and also the cycling rate, like C rate. So those things are very, very, very important. Like SOC and DOD, how much? Similarly, energy density of the battery is also very important. It's also called as sometimes specific energy and energy density. So the specific energy density is different for the different types of batteries. How those data or those values can fix to our EV so that we can run the EV without any problem. For example, you take a lithium-ion battery. Lithium-ion battery cost very high, and also the life cycle is also high. But you take lead acid battery, the cost actually less. Lead acid battery, different types of there, like VLR battery and other kinds of batteries are there. In between, we have like lithium-ion battery for the different kind of combinations also. But now the sulfur-based batteries are coming. There are the recent research stage. What their main role is to improve the cycle as well as reduce the cost. So with the existing lithium-ion battery, by adding some more materials, they are developing a very good batteries which are going to provide the increased life cycles, then with reduced cost. So let's see. So capital cost, cycle life, efficiency, SOC, C rate, they are all the very major things. When I go into work, this battery, anybody is interested, a lot of websites are giving the good idea, like batteryuniversity.com or some of the leading industries who are working on the battery. We have very good information. If you take lithium ion battery, the entire story is there, like the temperature, as well as the testing, as well as the life cycles, and how we are going to connect to the power electronic converters, what are the changes happening, life cycles. So many informations we are having with respect to the battery if we take to the EV system. Of course, next specific energy. I was just telling about specific energy, that is watt-hour per kilogram. So the specific energy is there actually. For example, if you take like lithium cadmium batteries and all, the lithium cadmium batteries and all is going to provide the range of 80 kilometer. See, the range is actually only 80. Or the cadmium, actually, so lithium cadmium is going to give a range of 80, but the specific energy is also very less. And if you're going to take about the recent batteries as coming called as lithium air as well as lithium sulfide, which are there in the right side, lithium air and the lithium sulfide. So the lithium air is going to range of nearly 500 or more than 500 kilometer, or lithium sulfide is going to give nearly 400 or more than 400 kilometers. But actually the specific energy also good, but we have to see the cost and all. That's what we are classifying into two category. One is the under development category, three category. Other one is actually the available and R&D. As I said, the lithium air or slightly lithium sulfur is under the R&D stage or under development stage, which including zinc air, the zinc air as well as the advanced lithium ion batteries. In the available range, actually, the range is there with more moderate range. Also, especially lithium ion. Lithium ion is the most convenient battery because it's going to give the range of nearly 150 to 160 or 170 like that. Followed by what's happening. Even the specific energy also almost moderate compared to the nickel cadmium or lithium air battery. So the batteries for the electric vehicles is the very very important thing. I'm not talking about technical part. This is actually basic things should be understand before going to take the technical part of this battery. So the battery, what type of battery we are using? When you're talking about the battery itself, the type, range, as well as the specific energy, then the state of charge, as well as the depth of discharge, SOC, DOD, those things also can be covered. In the data sheets, there are clear details are there. We can work for our simulation or our hardware. Then the motors. Of course, the motors, electric vehicle motors are very important for the motors. The first one is the motor. The first one is the motors. So basically, what we are using DC and AC type of motors, that we can tell it as actually commutator and commutatorless motor. When you talk about the commutator motor, actually DC, permanent magnet. Permanent magnet motor, followed by wound field type of motor. When you talk about the commutatorless motor, we have actually very basic induction, especially both wound and cage, squirrel cage type, and synchronous type when you're going to have reluctance motor as well as wound out, all those things. So the type of motor what they're selecting is also very important. It's not like simply we can select it, because how the power flow is between the battery and to the motor, what type of power converters we are using, or what type of drive system we are following up, including the battery. So those complete concepts can be derived when you're going to use this electric vehicle. That is actually. So here one more slide is there. That's going to discuss about this the torque. See, induction motor basically having less torque, especially when you're going to use EV. But the brushless DC motor having is good, but more than that, um, the IPM, that is called as induction power motor. So those motors are giving good torque also, but cost is very change. Also control. So when you're going to place the motor, Along with the Powertrain converters, the control is also there. Controller should be developed, because the controller, Powertrain converters is all interconnected towards to the EV system, right? So the proper controllers also should be developed in the kind of a motor. Generally, battery means lithium ion. In the motor means we are going for the BLDC, or very basically to test running purpose only. In the lab, we are using induction motor, that also we can use. In our lab, we tested this small induction motor, but we have faced some problems actually. So those things also there in respect to the electric motors. With this, before going to conclusion, I want to share some of our experience in which we are working in the EV. In our campus, actually Chennai campus, we have EV team, research team, like faculty team. So we taking the work actually with respect to the development of signal processing applications to the power converters actually, especially for the EV system. So what we are doing there, we are collecting the different data, as well as and with actually we have the students team also. Our team, we are working the IoT based signal processing used, actually the power converter state control technique we are using. We developed a very small three wheeler in which we can be able to transport the food from hostel to the mess. So those kind of setup we developed. It's very completely manufactured, as well as designed in-house project actually. So there the type of motor we are used, as well as the power electronics, everything we design in our lab. But the control completely happening with respect to the IoT, because we have actually a IoT, a smart system based lab. So there we are able to control the entire the EV. Even is now currently in the use, but we are going to also have the collaborations with some other industries. Like in Bangalore, we have going to have the Green Days Technologies Bangalore. Also, some of the industries, they are all connected as working with us to develop the EV system. But we are not in completely the developer stage of the lab. Only we developed the vehicle, since our campus is very new. With the help of the EC as well as mechanical students, we working on that. As well as also we are testing and the batteries also. We have a simply battery setup testing infrastructure. There, some of the industries coming for the consultancy. So there, small industries, medium industries. So we are developing the battery testing also. With that, we are taking some different data. So those data we are collecting, and we are going to work further by using some AI techniques and what kind of results we can identify to troubleshoot, as well as to find out the problems in the industry connecting with it. So these are all the things we are currently working in our campus. So with this, I want to conclude actually about whatever the topics we covered. First of all, I started with the history of EV, and followed by the importance of EV, especially the major challenges and opportunities in the electric vehicle, and the different fuel diversification of EV with respect to the conventional, then the advantages of EV. Later part, we moved to the power electronics part actually, that is DC-DC converters. So we have seen the DC-DC converters, the key role, which is connecting to the drive system, also which is connecting to the charging system. So, and then the charging infrastructures also we have seen, like a common AC bus as well as a DC bus. Then um, followed by we have seen actually the standards. Yes, why the standards are important? Like different standards are there. Like already the developed standards all over the international level, starting from the China, Japan, China, UK, as well as USA, CIE, then India, Department of Heavy Industries. So those standards, as well as upcoming standards, or the importance of standards also we have seen, we covered. Followed by the VTOS technology. Yes, the upcoming future trending method is actually VTS technology, because of the development of complete electric vehicle. Why can't we use optimizely this vehicle to X technology, grid, vehicle, home, load, like that? So VTS technology, but there's still in the VTS technology there are some issues are there, challenges are there. It's not reaching to the common people. So those things also we have seen. Finally, that is called as actually the importance of using wide band gap based devices of power electronic converters, rather than the conventional silicon based. Even the market capitalization also increasing, especially for the EV, when you're going to use this silicon carbide as well as gallium nitride, rather than the silicon devices, because of wide range of frequencies, including gigahertz range of frequencies. Followed by we also seen the batteries, especially different types of batteries, their specific energy as well as life cycles, cost, and which one is the currently trendy battery. And a lot of research is happening, upcoming stage, research stage, as well as already running the batteries. Those we have seen, followed by uh, followed by standards also, like how the EV can be implemented. So with this, I want to conclude today's presentation. Whatever I'm not showing the technical part. I was just giving only the overview of the powertrain converters, electric powertrain, simply electric powertrain of the system. Uh, Now I like to take, first of all, thank you for your patience. Almost 1 hour, 20 minutes from the moment we started the presentation. Thank you so much for all the participants as well as the organizers for giving me this opportunity. Now I'd like to take, as well as I would like to discuss and share the knowledge about EV system with respect to the team. Thank you so much.
Thank you, Dr. Lakshmanan, sir. It was informative talk actually. So now I would like to request the participant can have interaction with the expert now.
I think I can now stop sharing and I can come out, sir, like to answer.
Yeah, yes, sir. Yes,
Discuss,
sir.
discuss with the entire team. Yeah.
Yeah.
Am I audible?
Yes, sir, you are audible.
Yeah, yeah. Good afternoon, sir.
Good afternoon, sir.
Sir, I have some basic question.
Yes, sir.
So, have you encountered the advanced topologies which are used in the drives of for electric vehicles?
No, in this presentation I have not covered, but especially in the electric drive applications, multi-level inverters are the major role. We developed a cascaded 30-level bridge inverter also in our lab, especially for this. I said this like a three-wheeler, but and the control part still we are working, but the inverter is working well, and we are trying to connect that inverter output to the motors also. So yeah, our team is working as well as especially this multi-level inverters for the EV system.
Okay, sir. And as of now, we have seen 400-volt battery output voltage,
Yes.
and
Yes.
600-volt is also seen.
Yes,
So
yes, yes.
recently, also some of the major EV manufacturers are working towards 800-volt.
Yes, sir. Correct.
By looking at the topologies like NPC, that is neutral point clamp,
Yes.
which can support the 800-volt DC.
Yes.
So what do you see means? What are the other options which are available apart from NPC? Also, because this NPC topology is already patented one, and so if some researcher or if some person wants to do research in higher voltage that support the higher voltages, what
Yes. Yes.
are the points one should keep in mind while developing a suitable topology for,
Correct, sir.
let's say, 1000-volt battery?
Yes. 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 So I agreed, sir. Like you are telling very interesting point to all the participants also, like informative. Like NPC already developed with the 800 voltage level. So again, when I'm going to increase the voltage level, optimally we have to select a suitable converter also. Like in our experience, when our lab in our Powertrain lab we working on the cascaded edge bridge only, but we are trying to incorporate these ideas also. For example, the voltage level we are not tried, sir, actually in our lab so far. So, but we have read in the references literature, existing literatures like 800 voltage already the inverters have been developed. So the increasing the voltage level, we are planning to work as well as I think possibilities are there, like how effectively we are going to design the inverter with respect to all the controllers also in the closed loop.
Okay. Also, in one of your slide, that is slide number 19, I have seen that
Yes, sir.
you have used two boost converter back to back. One is working as a PFC and another one is working as a boost converter. So can't we use a single boost which can also work as a PFC as well as boosting the voltage?
We can use, sir. We can use. I'm just giving only the generalized diagram. We can use a single PFC, like
Yeah.
single boost converter for the charging purpose effectively without any problem.
Right. Right. Okay,
Because
sir.
in our, for some of us, the simulations long time back, we also tried that. It's working, sir.
Yes. Yes.
I hope I'm correct. If any suggestions, please let me know, sir. Like I'm sharing what is possible, sir. You are excellently
Right, sir.
explaining
Right, sir.
here.
Right, sir.
Thank you.
Thank you, sir.
Yeah, any other participants? We have enough time to discuss.
We are actually in our Coimbatore campus. We have industry supported, Robert Bosch supported electric vehicles lab. So what their people are doing, especially their mechanical research team, is working with respect to the battery charging and as well as battery testing on those things. Recently, the team from the Continental Bangalore, we started involving with Continental Bangalore, especially EV Powertrain. So the Coimbatore campus team, like our team from the Chennai only went to Coimbatore. So even I'm the part of the one. So the Continental Bangalore is supporting to develop, like our one of our participants said, Mr. Shivam, like they are going to support, but the development of material converters only. So what they're ultimately their aim is actually we have to develop effective powertronic converters which can support a large range of the large range of electric vehicles, including like bus or kind of things. Because optimistically, when I'm going to develop a large vehicle in the industry, they have a lot of challenges. So in that, they started giving one of the project which can support the large vehicle effectively. So that project recently sanctioned by the industry, and we are working on that also. But we didn't develop any hardware models. Only we started working on that simulation. But the support from the Continental Bangalore to our Amrita. And few more companies like nearby Chennai also, we are consulting them, especially for the battery management. Even the Tamil Nadu government recently planning to buy e-vehicles, e-rickshaws and all. So for that, they asked us to test and validate and give the certificates. So that process is going. Ultimately, we are also learning many things since we are the very 4 years old campus through our parent campus in the field of electric vehicles.
Yes, sir. It was good to know, sir. So I have one doubt, sir.
Sir, please.
Yeah. So the net zero emission, the term is now revolving around the globe very
Yes, sir. Yes, sir.
aggressively. So what is that? Is reducing CO2 or any other?
Of course, the zero emission is indicating that, as I mentioned in some of my slide, it's completely incorporating low carbon grid. It is covering CO2 emissions reduction level, as well as meeting the energy, meeting the power and the load demand, as well as smart system, like without intermittent power supply, which can also useful to. It's completely smart grid system. It doesn't mean that only the reducing the CO2. It's covering all the aspects, including generation as well as the transmission, distribution, and especially we are going to connect the EV, how it is happening. So those things are covering. Uh,
Net zero.
yes, yes,
Okay.
yes,
Sorry. So moving fully to EV,
yes,
the
sir.
developed countries such as Denmark, Norway,
Yes,
they
yes.
taken decision very fast and they did some good policy transformations. Then they achieved positively.
Mm-hmm.
But such large countries like India, China, even India, I can talk about, will be lagging that pace. So, what would be the
So
policy side? Yeah, yeah.
the main challenges actually in India we are going to face main first of all infrastructure. Even other than the technical part will develop very fast because we are all working very crisply towards the core research in the field of EV. But the infrastructure part, especially developing the charging infrastructure, and also the battery cycling recycling process, and policies also. Like if everybody, like now I'm going to buy a normal bike, Royal Enfield bike example, I can easily approach and get the details very quickly within half an hour. So like that, even I can get a very clarity like that in the EV in future. That should happen. The
Okay.
policies as well as the procedure should be cleared. Suppose I want to take the loan, yes, government is telling to give the loan, but the clarity, even officers are ready to explain, but how to approach, so there is a delay, a lag is there between the common public to the system. So that can be solved by connecting by with us to the closer to the EV, sir. That's what I feel from my side.
Okay. Yeah. Yeah. Thank you. Thank you.
Yeah. One question from one of the participants, that what is the motivation for using MLI in EV when we now have W band? Yeah, of course, W band devices are there, like wideband silicon carbide and silicon gallium nitride, but still to take and to supply a good sinusoidal input current to the induction motor, like a type of AC motor. When I'm going to also reduce the harmonics to the induction motor with the input current waveform. They still, rather than using the conventional two-level voltage source inverters, the material inverters, because ultimately the objective of material inverters will travel even for the EV also with presence of wide band gap devices. The quality, power quality, and also the efficiency of the entire EV can be improved, and the harmonics can be reduced since we are using the multi-row inverters for the EV system.
Hello, sir.
Sir, please.
Am I audible?
Yeah, you are audible, sir.
Yes, sir. Currently, the block diagram of the EV which you have shown, from that
Yes.
I can say that we are using two different circuit for the charging and motoring operation in the EV.
Okay. Yeah.
But
Yes.
we already have a three-phase inverter for the motoring operation. And
Mm-hmm.
when we want to charge our vehicle, at that time that three-phase inverter is ideal. So can't we use the two leg of that particular inverter as a rectifier in the charging circuit also? And in this manner, can we
Yeah.
reduce one converter in the entire
Yeah,
system?
we can use, sir, but when you're going to use the same converter for the for other applications also, like what you are telling, but the compatibility as well as the energy transfer, and without affecting the operation, we should follow it up. Because yes, inverter is there, but what kind of source we are using, like battery means we have battery only, of course. So with respect to the existing like voltage source inverter, the other possibilities also we are going to take, the technical interference we have to look into that at that time.
Okay. Thank you. Thank you so much, sir.
Yeah, thank you.
Yeah. Any other participants? Any interaction? Any question? Any comments? We have enough time. Okay. So Shivam, Dr. Shivam.
Yes, yes, yes.
So if there is any no question, shall we wind up? Yes.
Yes, yes. Sure, sure, sure.
We have, okay. Okay. So yeah, Dr. Lakshman, it was very good presentation. We have got many informations with your slides as well as the way you talked. It was so, even though it was second half, so you make us in vigilance. So the voice and the energetic way, I really felt positive way. Thanks for that. Yeah. So I'd like to request all the participants turn on their video just for take a photo with the expert speaker. Yeah. So with that regard, I like to dedicate one virtual token of appreciation to the expert speaker, Dr. Lakshmanan. I hope all are able to see. So on behalf of VIT, we like to give a virtual token of appreciation to our speaker.
Thank you, the entire team, TFAC Core Center.
Are you able to see, sir? Dr. Lakshmanan,
Yes,
sir?
I can able to see, sir.
Okay. Thank you so much, sir.
Thank you so much, the entire the team who given the opportunity for delivering a lecture. I hope the session was useful and probably it may bring a fruitful research collaborations among us. And thank you so much once again the entire the team head as well as the professors from the VIT University and all the participants. Let's hope positively, and we'll meet such kind of discussions in future also, and we can collaborate and work towards to strengthen and enhance the EV system to our society. Thank you so much.
Sure, sir. So one last request.
Sir, please.
So if you can share your email ID in the chat box so that if the participants face any doubts, they can contact.
Definitely. Sure. I'm just typing my email ID, official email ID. So this is my email ID. The participants, if any queries, let's contact in future also, and we'll work together. Thank you so much.
Yeah, sir, thank you, sir. Thank you, sir.
Thank you, Dr. Thiru, and the entire team. Thank you so much. Yeah. So if no queries, I can leave this meeting. Am I right, sir?
Yeah. Please, sir. Yeah,
please, sir.
Yeah, thank you. Thank you.
So we will have that another 1 hour talk at 5 o'clock.
Yes, 4:50 we should join again.
Okay. 4:50. Yeah.
4:50 p.m.
Yeah.
Okay, so I request the participants to join back again at 4:50 p.m. Thank you.
Thank you.
Thank you, sir. Thank you, sir.